Welcome back to the deep dive. Before we even really get into the topic today, I actually want to ask you to do something.
Oh, we are starting with an assignment.
Yeah, just a quick one though. If you are listening to this right now, I want you to just look around the room you are in.
Or your car, if you're driving.
Right, exactly. Look at the dashboard. Or if you are at home, look at your Wi-Fi router or your TV, maybe the charger block for your laptop.
Pretty much anything plugged into a wall.
Yeah, all of it. Because we live in this world that we generally define as solid state,
Mm.
right? Like we think of our electronics as these completely rigid, frozen blocks of silicon and plastic.
Just static things that process logic until the end of time.
Exactly. But the thing is, there is a component inside almost every single device I just mentioned, and honestly, it is highly likely it's inside the device playing this audio right now that completely defies that solid state logic.
It really does. It is the ubiquitous unsung hero of modern tech. And quite often, it's the inevitable point of failure.
We are talking about the aluminum electrolytic capacitor, or the ECAP. And I have to say, the more I read through the source material for this deep dive, the more I realize that this is not just some boring standard electrical component.
Oh, far from it.
It's a contradiction. It is literally a piece of 19th century chemistry living inside our 21st century digital tech. It's a component that relies on what the sources call useful rust.
Useful rust, yeah.
And essentially a wet sponge just to keep the entire internet running.
That is a really evocative way to put it, but it is completely accurate. I tend to treat our electronics as if they are immortal.
Right.
We expect a microprocessor to work flawlessly forever unless you take a hammer and physically smash it. But to actually power that processor, we anchor it to a component that is fundamentally strictly mortal.
It has a biological clock, basically.
Exactly. It has a lifespan. It ages.
Yeah.
It physically dries out.
And that was the hook for me. We are building these massive digital cathedrals, but the foundation has a ticking clock built right into it. So our mission today is to completely unpack the ECAP.
We have a lot of ground to cover.
We really do. We aren't just going to sit here and read a data sheet to you. We are going to look at the anatomy, which is way more complex than I ever thought, and the chemistry. And surprisingly, the history.
The history is wild.
Right, because it involves this massive industrial espionage scandal back in the early 2000s that honestly nearly took down the entire computer industry.
The capacitor plague. It is a classic cautionary tale of why you really shouldn't steal trade secrets if you don't actually understand the underlying chemistry.
We are definitely going to get to the exploding computers later, but I think we should start with the basics.
Good idea.
So if I crack open an old radio, or even just look through the vent holes of my desktop PC, I see these little cylinders.
Right, the cans.
Yet they look like tiny little soda cans just standing up on the green circuit board. Sometimes they have this plastic shrink wrap on them with numbers, and sometimes they are just bare, shiny metal. What exactly are we looking at there?
So visually, yes, they just look like little cans. But that aluminum can is really just the housing. It's the shell. The actual magic is all inside.
Okay.
If you were to take a pair of heavy pliers, which please do not actually do this at home because the stuff inside is highly caustic and it will make a mess. But if you did peel that metal can open, you would not find a solid block of material in there.
Right, the notes called it a jelly roll.
Yes, a wound roll. You would find a roll of foils. But honestly, calling it a roll of foil really undersells the engineering involved.
Because it's not just one piece of foil.
No, it is a sandwich.
Yeah.
It's a highly engineered sandwich that has been rolled up very tightly. You have an anode foil, you have a cathode foil, and you have a separator paper sandwiched right in between them.
Okay, so let's pause right here because this is where my basic high school physics brain gets confused.
Sure.
Standard capacitor physics, right? You have two metal plates, and you have an insulator in between them. You pump a charge into the plates, and the energy is stored in the electric field between them.
That is the textbook definition, yes.
So in my mind, looking at this jelly roll, the anode foil is the positive plate, the cathode foil is the negative plate, and that paper is the insulator.
And that right there is the most common misconception. Even a lot of first-year engineering students get that wrong on their first pass.
Really?
Yeah. Because if this were a film capacitor or a basic ceramic capacitor, you would be absolutely right. But in an aluminum electrolytic capacitor, the cathode foil is not actually the cathode.
Wait, hold on. It is literally labeled cathode foil in all the diagrams in our sources.
I know it is. It is incredibly confusing historical terminology. But you have to think about the physical structure of what we're trying to do here.
Okay.
To get high capacitance, which is just the ability to store a massive amount of electrical energy, you need a massive amount of surface area on your plates.
Right, bigger plates mean more storage.
Exactly. Now, if you just take 2 strips of completely smooth aluminum foil from your kitchen and roll them up with some paper, you have very little actual surface area.
Because it's just flat.
Right. You would get maybe a few microfarads of capacitance, even if you made the thing the size of a giant beer can.
But these E-caps are tiny. They're the size of a pencil eraser sometimes, and they have huge capacitance ratings. So where is all that surface area coming from if the foil is so small?
It comes from a process called etching. Before they even wind that roll up at the factory, they take the anode foil, just the positive foil, and they run it through an electrochemical acid bath.
So they are intentionally corroding it.
Yes, they essentially eat away at the solid metal. They roughen it up on a microscopic level.
The source material actually mentioned a magnification factor of up to 200. I was really trying to visualize that when I was reading it.
It's hard to wrap your head around.
Yeah, like if I have a completely flat sheet of foil the size of my dining room table, how do I suddenly get 200 tables worth of surface area just by scratching it up with acid?
You have to stop thinking in 2 dimensions.
Yeah.
You have to think in 3D. Think about a city map. Let's use Manhattan as an analogy.
Okay.
If you look at a flat paper map of Manhattan, it covers a very specific number of square miles. That is what engineers call the projected area, the footprint.
Right, just the outline of the island.
But now imagine I give you a paintbrush and I tell you that you have to paint every single exterior surface in Manhattan, every single side of every skyscraper, every window frame, every alleyway wall, down into the subway entrances.
Oh, wow. Okay.
How much paint do you need for that compared to just painting a flat parking lot the size of the island?
A massive amount, probably hundreds of times more paint.
Exactly. And that is exactly what the etching process does to the aluminum foil. It doesn't just put scratches on the surface. It digs these deep, microscopic vertical tunnels straight down into the aluminum.
Millions of them.
Billions. Billions of microscopic tunnels per square centimeter. The solid metal foil essentially becomes a 3-dimensional sponge of metal.
Okay, I am totally with you on the Manhattan analogy. That makes perfect sense. So we have this incredibly complex, rough metal sponge.
Right. Now keep that in mind. If you just took a second piece of flat aluminum foil, the so-called cathode foil, and laid it directly on top of that etched sponge, where would it actually touch?
It would only touch the very tops of the skyscrapers. It wouldn't get down into the alleyways or the tunnels.
Precisely. You would instantly lose all of that extra surface area you just spent all that time in acid creating. It would be completely useless.
So you need a second plate that can somehow conform to all those tunnels.
Yes, you need a second plate that can flow. You need a liquid.
Ah, the electrolyte.
The electrolyte. The liquid is the actual cathode.
Wow.
It literally floods the streets of Manhattan. It flows down into every single microscopic tunnel and coats the entire rough surface of the etched aluminum. That is why the liquid is the true second plate of the capacitor.
That clicks so perfectly now. So the liquid is the functional negative side of the circuit. But then, wait, what is the physical cathode foil actually doing in the roll? Why do we even need a second piece of metal in there at all?
Well, think about how you connect this to a circuit board. You cannot solder a copper wire directly to a liquid.
Right, that would be messy.
You can't just stick a metal lead into a wet sponge and hope for a reliable high-speed electrical connection. You need a physical way to get the electricity from the outside world into the liquid itself.
So the cathode foil is just the contact mechanism.
Exactly. It is like dropping a giant copper cable into the ocean. The salt water of the ocean is the actual conductor, but the cable is just the interface to get the power in and out.
So calling it the cathode foil is almost a lie. It's really just the current collector foil.
Current collector foil would be a much, much more accurate name from a physics standpoint, yes.
Okay, so we have this really rough metal sponge, which is the anode, and we have a liquid soaking deeply into it, which is the cathode. But wait, if the conductive liquid is physically touching the conductive metal, isn't that just a short circuit? Why doesn't the electricity just flow right through the whole thing?
And this brings us to the actual magic of the construction, the useful rust we talked about. We need a dielectric, an insulator to separate the metal sponge from the liquid cathode.
And in this specific case, it is aluminum oxide.
Yes, Al2O3.
Because aluminum inherently loves oxygen, right? Like if you leave a piece of bare aluminum outside in the yard, it instantly forms a thin oxide layer on its own.
Exactly. That is why aluminum doesn't rust away into dust the way iron does. It naturally protects itself with a very thin barrier.
But for a high voltage capacitor, I'm guessing that natural rust just isn't quite good enough.
Not even close. It's
Yeah.
way too thin and it's very patchy. We need to engineer a perfect layer.
So this is the anodization process from the outline.
Right, so before the jelly roll is even assembled, they take that rough, etched foil sponge and they run it through another chemical bath. But this time they apply a very specific voltage to it.
They force it to rust.
They force the oxygen in the bath to bond chemically with the aluminum surface. They grow a highly distinct, totally uniform layer of oxide over every single microscopic hill and valley.
And the sources noted this concept of a valve metal.
Yes, discovered way back in 1875 by a French physicist named Eugène Ducretet. He found that certain oxidized metals like aluminum or tantalum act like a one-way valve. They let current flow freely in one direction, but totally block it in the other.
Which is exactly what an insulator needs to do here. But the key to this whole thing is the thickness of that rust layer, right?
It is the most critical parameter. The thickness of this oxide completely determines the maximum voltage the capacitor can handle.
The notes literally say the thickness is measured in nanometers per volt.
It is unfathomably thin. And this is crucial for the performance because capacitance, the storage capacity, is inversely proportional to the distance between your two plates.
So the closer you can get the metal plate and the liquid plate together without them actually touching, the more energy you can store.
Precisely. You want the insulator to be as impossibly thin as you can make it without it breaking down.
I want to really get a solid sense of scale here for the listener. If I have a standard everyday capacitor, say one rated for 16 volts, which is super common in a lot of computer parts, how thick is that insulator layer?
Well, the general rule of thumb in the industry is about 1.4 nanometers of oxide thickness for every single volt of rating. So for a 16-volt capacitor, you are looking at roughly 22 to maybe 25 nanometers thick.
Okay, that number obviously sounds very small, but let's contextualize it. I looked this up. A single strand of human DNA is about 2.5 nanometers wide.
Wow. Okay, so if you do the math there, the physical barrier that is keeping your computer's power supply from instantly blowing up right now is only about 10 DNA strands thick.
That is terrifyingly thin.
It really is. It is walking an absolute molecular tightrope. And that is exactly why these components are so incredibly sensitive to voltage spikes.
Because if you push the voltage too high,
say you accidentally put 30 volts across that 16-volt capacitor. The electrical field across that tiny gap becomes so intensely strong that it physically rips electrons right through that thin oxide wall.
it just punches a hole right through it.
Yes, that is called dielectric breakdown,
And once you puncture that wall, you just have metal touching liquid.
which is a dead short circuit. Massive, unregulated current flow, incredible heat, and then a very fast explosion.
Yeah, we are definitely getting to the explosions. But before we leave the oxide layer, I want to touch on something the source material mentioned regarding the actual type of oxide they grow.
Well, the structural types.
Yeah, there was this big distinction between amorphous oxide and crystalline oxide. And reading it, it almost felt a bit like a personality test for the component.
That is a great way to frame it. It is entirely about the physical structure of the molecules in that rust layer.
So what's the difference?
Well, amorphous oxide is kind of like a massive pile of bricks just dumped haphazardly on the ground. It is disordered. It is structurally messy. But because it is so messy, it is actually very flexible.
It can shift around.
Right? It covers the rough etched surface incredibly well, and it is very chemically stable over long periods of time. This is the exact personality you want for a general-purpose capacitor that just needs to run quietly for 10 years.
The reliable, steady workhorse.
Exactly. But then, on the other hand, you have crystalline oxide. Imagine taking those same bricks and meticulously building a perfectly rigid, perfectly aligned wall.
Highly organized.
Everything is locked in place. Because it is so highly organized, it is physically denser, which means you can actually get away with a slightly thinner layer to get the exact same voltage protection.
Which loops back to our rule from earlier. Thinner gap means even higher capacitance in the same physical footprint.
Much, much higher efficiency, yes. But there is a huge trade-off. What happens to a perfectly rigid brick wall if the ground underneath it suddenly shakes?
It cracks. It doesn't bend, it just shatters.
It cracks. Crystalline oxide is incredibly brittle. If the machine bends the foil a tiny bit too much during the winding process at the factory, or even if the capacitor just heats up and thermally expands during use, that oxide can develop microscopic fractures.
So where do they even use the crystalline type if it's so fragile?
You typically only see it in very specialized high-voltage applications where you desperately need that maximum efficiency, things like photo flash capacitors for professional cameras. They need to sit there at 300 volts and then dump all that energy in a single millisecond.
Right, they need the pure performance and they just accept the fragility. So for my simple laptop charger, I am definitely looking at the amorphous type because I prioritize it simply not dying on me over it being perfectly space efficient.
Correct. You definitely want the amorphous stability for a daily driver.
Okay, let's move on to the liquid itself. We've been calling it the wet sponge, but it is obviously not just plain tap water in there, right? The source notes list some fairly intense chemicals like ethylene glycol and boric acid.
Right, the electrolyte. This is essentially the secret sauce of the entire industry. Every major manufacturer has their own highly specific proprietary recipe, and they guard those formulas like it's Coca-Cola.
Because it's a huge competitive advantage.
Massive. But historically, and honestly still very commonly today, the base liquid for that soup is ethylene glycol.
Which is literally car antifreeze.
Basically, yes. It is a solvent that doesn't boil off easily when it gets hot, and it doesn't freeze solid when it gets cold.
Perfect for an electronic component that gets hot.
Exactly. Then they take that base and they dissolve conductive salts into it. Very often things like boric acid or various ammonium salts, that is what actually makes the liquid conduct electricity.
The notes called this the borax electrolyte.
Yeah, it has been around since the 1930s.
Yes.
It's the gold standard for stability.
But the liquid does more than just passively conduct electricity. And this is the part of the deep dive that I found totally counterintuitive.
A self-healing.
Yes. The liquid is actually acting as a medic. It is a microscopic repair crew living inside the can.
This is arguably the single most important defining feature of the aluminum electrolytic capacitor. It is entirely why we still use them everywhere, despite all of their flaws.
But how does a completely lifeless chemical soup heal a scratch on a piece of metal?
Well, think back to that unimaginably thin oxide layer, the 10 DNA strands. It is practically inevitable that there will be microscopic defects in that wall.
Right. Impurities in the original aluminum or tiny microcracks from when they rolled it up.
Or just thermal stress over time. Now, in a solid-state capacitor like a ceramic one, a crack in the insulator is just a permanent path for a short circuit. It is game over for the component.
It's just dead.
But here in the ECAP, you have a conductive liquid physically pressing against that crack, and that liquid contains dissolved oxygen.
So when the electrical current tries to rush through that crack in the wall...
The current actually drives a chemical reaction. It's basically the anodization process happening all over again, but highly locally in real time. The leakage current literally forces the oxygen out of the electrolyte and binds it with the raw exposed aluminum at the very bottom of the crack. It dynamically grows fresh aluminum oxide, plugging the hole.
It literally scabs over.
Yes. It patches the breach, the leakage current stops flowing, and the capacitor just fixes itself while your computer is running.
That sounds absolutely perfect, almost too perfect. So what is the downside here? There has to be a physical cost to doing that.
The cost is chemistry. You do not get that fresh oxide for free.
Right, conservation of mass.
To make that Al2O3 molecule, you have to physically steer oxygen atoms from the electrolyte solution itself, which means every single time it heals, you are physically permanently consuming a tiny bit of the liquid.
You are using up the lifeblood of the capacitor just to fix the wounds.
Exactly. And there's a chemical byproduct to this process, too. When you strip the oxygen out of water or out of these solvents, what chemical element is left over?
Oh, hydrogen.
Hydrogen gas.
So every time the capacitor patches a tiny microscopic hole, it generates a tiny microscopic bubble of hydrogen gas inside the sealed can.
Yes.
And since the can is hermetically sealed, that gas has absolutely nowhere to go.
Correct. Now, if the healing process happens very slowly over years, that gas might just reabsorb into the liquid or diffuse out incredibly slowly through the rubber seal at the bottom.
But if it's happening constantly...
If you have a ton of defects, or if you are running the capacitor really hot and accelerating the chemistry, the hydrogen gas builds up pressure fast. It essentially turns the tiny aluminum can into a pressure cooker.
Okay. This feels like the absolute perfect transition to the history segment of our deep dive, because the phrase pressure cooker literally describes the entire computer industry in the early 2000s perfectly. I want to talk about the capacitor plight.
This is a story that I think really highlights exactly how incredibly fragile our entire global technology supply chain actually is.
So set the scene for us here. The year is roughly 2001.
Right. The tech world is absolutely booming. The dot-com crash happened, but hardware is pushing forward fast. processors are getting much, much faster. The Pentium 4 is just coming out.
Huge power draws.
Yes, these new, extremely dense processors needed a ton of power, and they needed it delivered in microsecond bursts. To do that, the power supplies on the motherboards desperately needed capacitors with incredibly low electrical resistance.
Which the industry calls ESR. We will define the physics of that in a bit. But basically, they needed high-performance sports car capacitors.
Right. Now, if you are a chemist and you want to lower the electrical resistance of your electrolyte, the absolute easiest knob you can turn is to just add more water to the recipe.
Because water conducts really well.
Much better than the thick glycol, yes. But water is incredibly dangerous inside an ECAP because pure water aggressively attacks bare aluminum.
It just rusts it continuously.
It corrodes it, constantly creating hydrogen gas, even when the device is completely turned off. So adding water was always seen as a huge no-go. But then a highly respected Japanese component company called Rubicon managed to develop a revolutionary new formula.
They cracked the code.
They did. It was a very high water content electrolyte. But they had discovered this complex proprietary mix of chemical additives inhibitors that successfully neutralized the water. It completely stopped it from eating the aluminum.
So they got all the performance of the water with none of the explosive downsides, the holy grail.
It absolutely was. And naturally, every single competitor in the market wanted that formula desperately. And this is exactly where the spy enters our story.
A rogue material scientist.
Allegedly, yes. A researcher from a competitor. The exact details get murky and stories vary. Some sources say they defected to a Chinese manufacturer. Others point to a Taiwanese outfit often cited in the industry as Luminous Town Electric.
But the core gist is they walked out the door with the golden recipe.
They stole the formula, yes.
But they messed up the heist.
They really did.
Yeah.
Because they didn't steer the complete formula. They got the base recipe perfectly, the exact ratios of water, the solvents, the primary salts. But they seemingly missed the supplemental page with the proprietary stabilizing additives.
Or they just completely misunderstood how the additives interacted.
Right. It's like breaking into a vault to steal a famous recipe for a loaf of bread, but you completely forget to write down the yeast.
Or honestly, in this context, it's more like stealing the blueprints for a bomb and completely forgetting to build the timer mechanism.
That is unfortunately a much better analogy, because this competitor took this flawed, deeply unstable recipe and they just started manufacturing these defective capacitors by the absolute millions.
And because they were stealing the tech, they undercut everyone on price.
They sold them to major assembly houses at a massive discount. And those assembly houses were building boards for everybody. They put these ticking time bombs into everything.
Bell Optiplex desktops, Apple iMac G5s, HP workstations, networking gear, everything.
And the truly insidious part of this whole plague is that the capacitors actually work perfectly at first.
They passed all the factory testing.
They passed the quality control checks with flying colors because the pure water corrosion reaction is relatively slow. It takes months of heat and chemistry to build up the pressure.
So the computers all ship out to customers. They get set up on office desks around the world. And inside every single one of those little cans, the highly unstable water is just slowly, relentlessly eating away at the aluminum foil.
We can actually do a quick chemical equation check here from the sources. It's 2Al plus 6H2O yields 2AlOH3 plus 3H2.
Right, so aluminum metal plus the water equals aluminum hydroxide plus that dangerous hydrogen gas we talked about earlier.
Exactly. The pressure slowly built up and up and up. And then right around 12 to 18 months after these machines were sold pop.
Yeah, I distinctly remember working in an IT support job around that exact time. You would open up a desktop computer case that had just stopped booting, and it genuinely looked like a microscopic war zone in there.
It was a mess.
The shiny silver tops of the capacitors were all domed and bulged outward, or they had literally split wide open and spewed this completely dried up brown, crusty chemical stuff everywhere.
And that brown crust was the conductive electrolyte itself. It physically sprayed out onto the sensitive motherboard traces, totally shorting out data lines, killing the CPU, killing the memory.
It was devastating.
It cost the PC industry billions of dollars. Dell alone had to take a massive financial gutter. Hit some estimates, put it in the hundreds of millions, just replacing thousands and thousands of ruined motherboards under warranty.
All because one person stole a chemical formula they simply didn't understand.
It is the ultimate lesson in the difference between know-how and know-what. They knew what physical chemicals were in the jar, but they had absolutely zero idea how they work together dynamically.
That really drives home the reality that these little cylinders are not just static buckets holding electricity. They are highly active little chemical reactors.
They're entirely alive in a chemical sense.
So let's pivot and look at the actual parameters, the personality traits of these capacitors, because really knowing these traits helps us fully understand why they eventually fail, even when there isn't some botched stolen formula involved.
Let's do it.
Let's start with polarity. We mentioned the valve metal concept earlier, the one-way street.
Yes, aluminum electrolytic capacitors are strictly polarized. They have a very distinct physical positive and a distinct negative lead. You absolutely cannot mix them up when you install them.
What actually happens physically if I just grab a soldering iron and put one in backward on a circuit board?
It is catastrophic almost immediately. Remember that thin oxide layer, the insulator wall, is originally formed at the factory by applying a strong positive voltage to the anode foil. It is an active electrochemical growth process.
Right.
If you apply a massive reverse voltage, meaning you push a heavy negative charge into that positive anode, you actively reverse that entire chemical process. You start aggressively, actively dissolving that oxide layer right back into the liquid.
You are literally stripping the insulation right off the wires while the power is on.
Exactly. You are stripping the insulation. And at the exact same time, the chemistry starts desperately trying to form a brand new oxide layer on the actual cathode foil, which was never designed or etched to handle it.
So the electrical resistance just plummets to near zero.
It drops instantly. The current wildly spikes, and all that energy dumps straight into the internal liquid. It hits the boiling point almost instantly.
And the gas pressure.
It goes completely off the charts in seconds. The aluminum can will physically violently explode.
Which brings up a very noticeable visual feature. This is exactly why they have those score marks stamped into the top of the can, right? Like if you look closely at the top, there is always a little K shape or a Y shape physically dented into the shiny metal.
The safety vent, yes. It is a highly engineered, controlled structural weakness.
It's a blowout panel, basically.
Exactly. The engineers designing these know perfectly well that if the internal pressure gets too high, the can will absolutely fail. They can't stop it. So they want to deliberately decide how it fails.
Because the alternative is terrifying.
Right. Because without that weakened vent score, the entire aluminum shell might just rip off the bottom seal and shoot straight up into the air like a bullet. It literally becomes a metal projectile inside your TV.
Wow. But with the vent.
With the vent, as the pressure builds, the metal just bulges and then neatly tears open right along those stamped lines. It's safe. It is the absolute best way to visualize it. Think of an ideal, purely theoretical capacitor. It would store energy and release energy with absolutely zero loss. It would be a completely frictionless bucket of electricity.
But the real world has friction.
Right. In a real ECAP, the liquid electrolyte inherently has some electrical resistance. The paper spacer blocking the path has resistance. Even the physical crimped connection between the internal foil and the external metal leg has resistance.
And ESR is just the grand total of all those little obstacles added up.
Yes. It is the sum total of friction.
And basic physics tells us that whenever you push an electrical current through a resistance, you generate heat.
Correct. And this directly leads us to the next massive parameter, the ripple current. This is the parameter that usually silently kills capacitors in modern power supplies over time.
Because in a computer power supply, the capacitor isn't just sitting there full. It is constantly rapidly charging and discharging, hundreds of thousands of times every single second, just to smooth out the choppy voltage coming from the wall.
It's working out constantly.
It is a high-intensity interval workup that never stops. And all that moving charge is what we call ripple current.
And every single time that current sloshes back and forth, it is physically pushing against the ESR friction, which generates internal heat. If the inherent ESR of the part is too high, or if the ripple current demand from the processor is too punishing, the capacitor simply heats up from the dead center inside out.
And as we keep saying, heat is the absolute enemy of this component.
Heat is the ultimate killer. We will look at the exact math of the Arrhenius equation in a minute, but the short version is, heat physically makes the wet electrolyte evaporate faster.
And as it turns to vapor and slowly escapes,
there is physically less conductive liquid left inside to carry the electricity. So what happens to the friction?
The resistance, the ESR, goes even higher.
Exactly, the ESR goes up, which generates even more heat for the exact same amount of ripple current.
Which immediately causes even more rapid evaporation.
It is a totally inescapable thermal death spiral once it starts.
Okay, there is one more parameter we need to cover before we move on to predicting failures. And honestly, this one sounds like a ghost story from the source material. Soakage, or dielectric absorption.
Oh, yeah. It is a physical phenomenon that genuinely terrifies anyone who works on old high-voltage tube amplifiers or massive industrial power grids.
Let's lay out the scenario.
Imagine you are repairing a massive amplifier. You have this big capacitor sitting there fully charged up to 400 volts. You do the safe thing. You turn off the wall power. You take a heavy screwdriver with a thick insulated handle, obviously, and you carefully short the two metal terminals together to completely discharge it.
Right, you hear the big crack, the spark jumps, and the voltage drops instantly to zero. You think the bucket is completely empty and safe.
It is empty. So you walk away to go have a sandwich. You come back an hour later. You reach down to unscrew the terminals, and the second you touch the bare metal, you get a massive, dangerous electric shock.
Where did the voltage come from? The zombie voltage. Where was it physically hiding for an hour?
It was hiding literally inside the molecular structure of the oxide dielectric.
Really?
Yes. When you pump 400 volts into a capacitor for a long time, you aren't just piling loose electrons onto a metal plate. That intense electric field physically stretches and aligns the actual molecules inside the rigid aluminum oxide layer. It polarizes them physically.
Like bending a spring.
Exactly. When you short the terminals with the screwdriver, all the loose surface electrons leave instantly. The voltage reads 0. But those stretched oxide molecules take a long time to relax back to their normal neutral state.
And as they slowly relax?
As they slowly untwist over the next hour, they physically release their stored mechanical energy back onto the metal plates as an electrical charge. The voltage literally magically creeps back up out of nowhere.
That is just wild. It is like pushing down hard on a memory foam mattress. You take your hand away and it leaves an imprint, but then it very slowly, agonizingly, slowly pops back up to full size.
That memory foam analogy is absolutely spot on. Engineers actually call it dielectric memory. And it is entirely why, if you ever look at incredibly large industrial capacitors shipping from the factory, they almost always arrive with a thick piece of copper wire firmly twisted across the two terminals, shorting them out.
Ah. Because if they ship them in an open circuit, the tiny bits of static electricity from the factory or atmospheric changes could slowly build up via that soakage effect.
Exactly. The capacitor could literally slowly charge itself up in the cardboard box and potentially lethally shock the guy unpacking it a month later.
Okay, that is properly spooky. Let's move into the final major phase of this deep dive. Failure and reliability.
The inevitable end.
Right. We know perfectly well that these ECAPs fail. We've talked about how they dry out and pop. But from an engineering standpoint, how do we actually predict when that is going to happen? The source material leans heavily on this concept of the bathtub curve.
The bathtub curve is really the fundamental standard reliability model for almost all electronics. Imagine the physical cross-section shape of a bathtub graph.
Okay, so high on the left, dips down low and flat in the middle, and then spikes back up high on the right side.
Right, so that steep high wall on the far left side is what engineers call infant mortality.
That is a grim industry term.
It really is. But it describes failures that happen almost immediately right out of the factory box. These are sheer manufacturing defects. A completely bad rubber seal, a tiny scratch on the foil, a short circuit in the internal winding.
Stuff that was just built wrong on a Tuesday.
Exactly. And honestly, usually these are caught by the manufacturer during a process called burn-in before the part even ships, but a few always sneak through.
Then you move past that and you hit the long, flat bottom of the tub.
Right. This is the random failure phase. During this period, the component is working exactly as intended. The statistical failure rate is incredibly extremely low. If something dies here, it's usually just a totally random lightning strike or a power surge kind of event.
And for a lot of purely solid-state parts, like a simple carbon resistor or a basic silicon transistor, they just stay on that flat bottom practically forever, right?
Pretty much, yes. They don't really have a steep wear-out wall. They just keep going until some random external event finally kills them 50 years later.
But the electrolytic capacitor is entirely different.
It hits the right side of the bathtub, the wear-out phase. Because of the wet liquid electrolyte, the ECAP actually has a rigidly defined physical end of life.
The great drying out.
Yes. The rubber stopper sealing the bottom of the can is a very good polymer, but on a molecular level, it is not completely perfect. Over 10, 15, 20 years, the microscopic vapor in the electrolyte simply diffuses right through the solid rubber molecules.
It just walks right through the seal.
It does. It leaves the can forever.
Mm-hmm.
The capacitance value drops off a cliff. The ESR skyrockets to massive levels, and the circuit completely stops filtering electrical noise.
And we can actually accurately predict exactly how fast that evaporation happens using the Arrhenius equation. Now, I'm not going to ask you to do complex calculus on audio, but I really want to understand the core concept here, because this isn't just some loose rule of thumb. This is hard physics.
It is fundamental baseline chemistry. A Swedish chemist named Svante Arrhenius figured this math out way back in the late 1800s. The equation simply describes exactly how chemical reaction rates change radically with temperature.
Okay, so how does that apply to our wet sponge inside the can?
Think about the actual individual molecules swimming around in the liquid electrolyte. Scientifically speaking, physical temperature is nothing more than a direct measure of kinetic energy. It measures exactly how fast those little molecules are vibrating and violently banging into each other.
Right, hotter molecules just dance much faster.
And crucially, when they dance faster, they collide with much more force. Most chemical reactions, like the slow, corrosive breakdown of the electrolyte or the evaporation process itself, require a very specific threshold amount of collision energy to actually happen. Chemists call that the activation energy.
Like a toll booth you have to pass through.
Exactly. When you raise the overall temperature of the computer case, you are giving billions of more molecules enough kinetic energy to smash through that toll booth and react.
So even a fairly small bump in temperature can suddenly lead to a completely massive spike in the speed of the chemical reaction.
It changes exponentially, yes. And this elegant bit of physical chemistry translates directly into what the engineering world calls the 10-degree rule.
This is the golden rule of electronics right here.
It is. The rule states very simply, for every single 10 degrees Celsius you drop the operating temperature of an electrolytic capacitor, you exactly double its expected physical lifespan.
That is just a massive lever to pull.
It is the biggest lever you have. Let's actually do the rough math here to show how crazy it gets. Yeah. Let's say you buy a very standard ECAP. The data sheet says it is rated for 2,000 hours of life at its maximum temperature of, say, 105 degrees Celsius.
2,000 hours really does not sound like very much time. That is what, like maybe 83 continuous days?
Right, just under 3 months.
If I bought a brand new router and it died completely in 83 days, I would be absolutely furious.
Well, of course. But the trick is that inside your router, sitting in your cool living room, it is nowhere near 105 degrees. Hopefully, it is operating at a nice, mild 45 degrees Celsius.
Okay, so how many 10-degree steps is that? The difference between 105 and 45 is exactly 60 degrees.
Yes, 60 degrees.
Yeah.
Which is exactly 6 10-degree intervals.
Yes.
So according to Arrhenius, we get to double our baseline, 2,000 hours, 6 separate times.
Okay, let's double it. 2,000 becomes 4,000. 4 becomes 8,000.
Yeah.
16, 32, 64. All the way up to 128,000 continuous hours.
And if you divide 128,000 hours by the number of hours in a year?
You get just about 14.6. Let's round to 15 years.
Exactly. About 15 years of continuous 24/7 operation.
That is truly incredible. So the literal difference between your expensive device dying in 3 measly months versus it happily running for 15 straight years is literally just keeping the room cool and ensuring airflow.
That is exactly it. This is precisely why dust accumulation is such a massive silent killer of electronics.
It acts like a sweater.
It is a perfect insulating blanket. If your PC exhaust fans get heavily clogged with dust and dog hair, the internal ambient temperature easily, slowly rises by maybe 20 degrees Celsius.
2 10-degree steps.
Yes. You just quartered the total lifespan of your entire power supply. You dropped it from 15 years down to less than 4 years just because of some dust.
So honestly, the most practical takeaway here is clean your fans, people. Just buy a can of compressed air.
Seriously, it saves hardware.
So there's one more truly bizarre failure mode I want to touch on from the outline. Storage rot.
Ah, the shelf life problem.
Right. This is definitely one for the antique radio restorers or the retro computing nerds listening.
Yeah.
If I go into my grandparents' hot attic and I find a totally gorgeous, pristine vacuum tube radio from 1950, why shouldn't I just take it downstairs and immediately plug it into the wall socket to see if it works?
Because the capacitors inside it have essentially been asleep for way too long. Yes. When a wet aluminum capacitor just sits on a shelf, completely unpowered, with 0 electrical volts pushing through it for several decades, the liquid electrolyte, which remember is a mildly acidic soup, just sits there and very, very slowly eats away at our precious aluminum oxide layer.
The useful rust just dissolves away.
It does. With no leakage current to trigger the self-healing METIC process, the thin insulation wall just gets thinner and thinner and thinner until it's basically bare metal again.
The protective wall just crumbles into the moat.
Exactly. So if you just enthusiastically plug that antique radio straight into modern wall power, you are instantly violently hitting that completely weakened microscopic wall with hundreds of volts instantly.
It has zero chance of holding that pressure back.
None. The internal leakage current will be massive. The electrolyte will hit a rolling boil in a matter of seconds, and those old metal cans will just dramatically explode right there on your workbench.
Wow. Okay, so if I can't just plug it in, how do we safely wake the machine up?
You have to perform a process called reforming. Honestly, it is very much like incredibly slow physical therapy for a totally atrophied muscle.
How does that work?
You hook the old equipment up to a specialized variable power supply, usually called a variac. You start at absolute 0 volts, and then very slowly over the course of many, many hours, you dial the voltage up manually. You give it 10 volts. Then you wait. Then 20 volts.
So you were just gently nudging the chemistry.
Yes. This incredibly slow, gentle, creeping voltage gives the dormant self-healing mechanism the actual time it needs to kick in and work. It slowly drives the oxygen out of the old liquid and forces it to painstakingly rebuild the oxide wall atom by atom before the internal heat can ever get out of control.
You were literally nursing the chemistry back to health.
You are. And honestly, if you do it patiently enough and the rubber seals haven't totally failed, a 50-year-old capacitor can often wake up and work just absolutely fine.
That is genuinely surprisingly touching for a hardware discussion. It really strongly treats the little electronic component like a living biological thing that just needs some tender care.
It's an electrochemical ecosystem in a tiny jar.
Okay, so bringing this all fully together, we have explored this completely humble, mundane component. It is a piece of metal etched like the streets of Manhattan. It is coated in a nanometer-thin layer of engineered rust. It is filled with heavily modified car antifreeze, and it continuously heals its own wounds until it finally completely dries up and dies.
That is the perfect summary.
So the obvious closing question is, why are we still using millions of these things? Why haven't we just entirely moved on to something definitively solid state by now? Like the sources mentioned solid polymer capacitors or pure tantalum ones, why stick with the wet soup?
As with almost everything in engineering, it always aggressively comes down to two inescapable things: energy density and sheer cost, specifically when dealing with very high voltages.
So those newer techs just can't compete there.
Not perfectly, no. Solid polymer capacitors are genuinely amazing. They are completely solid, they have ultra-low ESR, and they flat out do not dry out over time. But physically manufacturing them to reliably handle high voltages, anything significantly above, say, 35 volts, gets incredibly difficult, bulky, and insanely expensive.
And what about tantalum?
Tantalum capacitors are incredibly dense. You can store a massive amount of energy in a tiny, tiny grain. But tantalum is a rare, expensive conflict mineral. And crucially, well, if a solid tantalum capacitor fails from a voltage spike, it doesn't just quietly vent some fishy steam. It tends to violently, aggressively catch fire and burn a hole through your motherboard.
Okay, yeah, actively catching fire is definitely not ideal for a laptop charger.
No, it's not. So despite all of its weird liquid quirks, the classic wet aluminum electrolytic capacitor is genuinely still the absolute undisputed king of the power grid. It is still the only available technology that can reliably hand you hundreds of microfarads of storage at 400 volts for just a few pennies per unit.
It really is the ultimate triumph of perfectly good enough.
Good enough is the true core driver of all industrial engineering.
It really is. So as we fully wrap up this deep dive today, what is the biggest ultimate takeaway for you personally from all these sources? We have gone so deep into the microscopic chemistry and the Arrhenius physics. What stands out?
For me, honestly, it is just about firmly breaking that psychological illusion of the perfectly clean black box. We as consumers tend to treat our sleek, modern electronics as these sterile, perfect logic magic boxes. But when you really fundamentally understand the ECAP, you realize that sitting inside that beautifully machined, sleek aluminum laptop charger, that ultra-thin flat-screen TV, there is an incredibly messy, highly active, wet chemical reality. There are physical ions frantically swimming around in there. Chemical gases are occasionally being vented. Molecules are violently vibrating with heat. We haven't actually escaped the messy physical world of chemistry at all. We've just brilliantly engineered a way to cleanly package it into tiny little sealed metal cans.
I really love that perspective. It honestly makes the high-tech stuff feel so much more incredibly grounded in reality.
It does.
And I actually want to leave the listener today with this final, slightly provocative thought, a bit of a philosophical hardware paradox to just chew on. We spend so much of our daily modern lives completely striving for absolute digital perfection. We demand completely lossless high-res audio. We want absolutely flawless 4K streaming video. We want mathematically perfect error-corrected code. We fundamentally want our digital data and our memories to be immortal.
We really do. We demand permanence.
Right. And yet the very fundamental thing that actively physically powers this entire modern quest for digital immortality is a cheap little component that fundamentally operates on the basic principle of inevitable decay.
Entropy always eventually wins the long game.
Your entire pristine digital life is quietly, silently sustained by a very slowly evaporating pool of liquid. It is entirely governed by the cold math of the Arrhenius equation and the sheer physical integrity of a 20-cent piece of stamped factory rubber. In a very weird way, every single massive multi-billion-dollar server farm and every single supercomputer on Earth has a very real biological heart hidden inside it. It beats, it ages, it slowly degrades, and eventually it just stops.
That is a deeply profound and admittedly slightly anxiety-inducing perspective to end on.
I like to keep people thinking. So seriously, go grab a flashlight and check your really old networking electronics for bulging tops. Give a quick little nod of genuine respect to the chaotic 19th century chemistry silently, fiercely bubbling away right inside your power brick right now. And please, for the love of your hardware, keep those exhaust fans clean. Thanks for listening to this deep dive.
See you on the next one.